Good morning. Let us discuss about the magnetic scalar and vector potential. Here the mathematical expression for the scalar and vector potential is given as del cross del V equal to 0 and similarly del dot del cross A is equal to 0, where A is the vector potential and V is the. The above condition discuss about H is equal to minus del Vm if the current density is 0. Therefore, del minus del Vm can be taken as del cross H equal to 0, that is J is 0. Therefore, del cross minus del Vm is equal to 0. From this we got del square Vm is equal to 0. Similarly, we can in magnetostatic field we can found the magnetic potential A as vector magnetic potential A as B equal to del cross. The scalar potential for line current, surface current and volume current is given below. Here A equal to line integral of mu naught IDL by 4 pi r. And similarly, for surface current A equal to surface integral of mu naught K ds by 4 pi r, and similarly for volume current A equal to volume integral of mu naught J dV divided by 4 pi r. Similarly, the magnetic flux density can be written as mu naught by 4 pi line integral of IDL cross r divided by r. Let us discuss about magnetic torque and moment. To define torque, torque means force into distance. Here in magnetostatics, the torque is defined as force into moment. The moment is taken as r and the force is F, which is shown in this equation. The unit of force is Newton and the distance, that means moment, is taken as meter. Therefore, the unit of torque is Newton meter. To determine the force and torque acting on a magnetic material due to magnetic field, consider a rectangular loop which is placed inside a magnetic field with flux density B. If you kept a current carrying conductor inside a magnetic field, it gets rotation. That means some forces act on the rectangular loop. One force is on upwards and another force is downwards. Both have equivalent magnitude. Hence, the rectangular loop rotates. This force can be taken as F equal to I line integral of dl cross B plus I integral of dl cross B. If dl is equal to dz and B is equal to B, substitute the value instead of dl as dz, you got like this. First, it starts from force F naught upward plus, so 0 to L, which is 0 to 2, which is the 0 to L, that is the length of the rectangular loop. And again L to 0, L is the length of the rectangular loop, which is the return force, which is given as this. The resultant force F equal to F naught minus F naught, that is equal to 0, and F naught is taken as IBL. The torque can be written as F into W sin alpha, which is from the figure. Substitute the value of force in the above equation, you got torque T equal to BIL W sin alpha. The BIL is the value of force. Next, let us going to discuss about magnetic boundary condition. Boundary condition can be taken between the two dielectric medium. Here, before going to check about the magnetic boundary condition, let us discuss about magnetic materials. There are three types of magnetic materials: diamagnetic, paramagnetic and ferromagnetic material. The example for diamagnetic is bismuth, gold, etc., and paramagnetic air, aluminum, platinum. Similarly, for ferromagnetic, cobalt, nickel, where ferromagnetic is the mostly used magnetic material, which can be defined by the permeability of each type of materials. Magnetic flux density can be defined as m equal to psi mh, where chi is the magnetic susceptibility. The symbol is stamped as chi. We know that magnetic flux density B equal to mu h plus mu naught into m. M equal to psi h. By substituting this, we have the relative permeability mu r. Let us going to discuss about the magnetic static boundary condition. In magnetostatic boundary condition, there is two medium 1 and medium 2. Here, consider a rectangular loop to construct the tangential component, and another one a pill box to make the condition about the normal component. By Ampere's law, we know that integral h dot dl equal to I enclosed. The current enclosed by the path is given as k delta w. Substituting the values along the rectangular loop ABCD, we have integral h dot dl equal to h t1 into delta w. And for path 2, we got the integral h dot dl equal to minus h1 plus hn2 into del h by 2. For path 3, minus ht2 into del w, and path 4, we have the value as hn1 plus hn2 into delta h by 2. By considering the above equations and equating it in the equation number 1, we have ht1 minus ht2 equal to k. Therefore, in magnetic boundary condition, the tangential component is discontinuous. If k equal to 0, the tangential component may be. Similarly, let us check for the normal component after substituting the values of. For normal component, let us consider a pill box as shown in this figure, which have a surface area delta s and the height be delta h, which is in medium 1 it have delta h by 2, and in medium 2 it have delta h by 2. The upper surface is shown the medium 1 and the lower surface is shown the medium 2. By substituting the values in medium 1 and medium 2 in the above equation, we got integral b dot ds is equal to integral b n1 into ds plus b n2 into ds. That can be taken as b dot ds is 0. 0 is equal to b into delta ds plus b n2 into delta s, which can be taken as b n1 minus b n2 into delta s is equal to 0. Therefore, b n1 is equal to b n2. In magnetostatics, the normal component across the boundary is. Let us consider for the normal component of magnetic field intensity. Here we can choose the magnetic field intensity by the normal component of magnetic flux density as b equal to mu h. By substituting this, we got instead of b n1 mu naught mu 1 into h n1 and b n2 mu naught mu 2 into h n2. From this we have h n1 and h n2 are not equal because the mu 1 and mu 2 the permeability of two mediums are variable. Therefore, h n1 is not equal to h n2, that is the normal component of magnetic field intensity across the boundary is discontinuous. It is not continuous. Thank you all.